So in the previous video we had looked at the results from a set point analysis and figured out why sometimes it provides results that are unexpected. In this example we had a set point for the room temperature that suddenly went to 90 degrees, and we had forgotten to add a filter for occupancy, so we were looking at nighttime results. First thing we're going to do is add that filter. So I'm going to make it a schedule filter and call it occupancy. And then I'm going to add not random values, but I'm going to add values that are pretty standard because we didn't get equipment in this case that we could use. So I'm going to assume that the facility is occupied from, let's say, 7 a.m. to about 6 p.m. and Monday, Tuesday, Wednesday, Thursday, and Friday. So a fairly default type of schedule, but probably more realistic than what we had before, which was 24/7 and similar to the set point. And I'm going to call this occupancy. So it looks like we needed to make a couple manual corrections. I'm going to now apply that filter to the various channels in here. So we had them already selected dynamically. I'm going to now add this filter. I'm going to do that for all the various channels. The weekend is now gone, so this clearly was the large portion where we saw erroneous or unexpected results was the weekend. So that explains some of the results. Okay, so I'm going to come back in a second when all these are done. Okay, having applied the filter to all the trends in this chart, we can now look at the weekdays post the weekend. Here's the weekend, no more data there, and then back from Friday to Monday. So the weekdays now look a little better behaved than before. Next thing we're going to do is rerun the set point analysis, but now with the set points instead of assigned to the set point trend that was in the data set, I'm going to go back and default to the fixed set points that I can use instead. So I'm going to use 68 for the heating and 75 for the cooling set point, just because I don't trust the trend that was actually automatically given, and reanalyze. So there's the data set. I'm going to do the same thing as before. Copy, shift select all the way down, and then copy, switch to Excel, and paste the data set again. Just like before, I'm going to assign the filter so I can sort, and the worst overall performer is now a different zone than before, and the result score is also much lower. It's 2.9 instead of 14. It also has a 0 score for the lower value result. That means it's never too cold. So the 2.9 upper value result is also the same as the overall result, because basically it's an addition of the two results that makes the overall score. So this zone, the worst overall performer, is now a zone that gets a little too warm. It gets too warm by 3.6 degrees on average when it's being analyzed. So let's take another look in the template graphs to see, again with a little bit of common sense, how these numbers look when we take a look at them in a graph. So open the chart again, and we'll switch it from the previous worst performer 5221. And there's 5131. A little bit odd that on the first 2 weeks there, we're looking at about 3.5 weeks of data. The first 2 weeks, the airflow and room temperature set points, everything is flat, almost as if they were, invalid data. Again, not uncommon. Many data sets contain, either illegal or partly valid data. So it looks like the UT has done its job correctly in assigning this zone a score of too hot, because obviously that room temperature we're looking at here is 79 for 2 weeks. But even then, after that fixed value ends and we're going to a variable values, it's still above 75. So that zone is marked as too hot, and it clearly is somewhat too hot, but not terribly too hot. It's a couple of degrees over set point, and that means all of the other zones are better than this zone. So let's go back to the spreadsheet here. This was earlier we sorted for the upper value result. So now let's look for the lower value result to find the coldest zone. Incidentally, we're doing this in Excel. We can also do it in the UT itself. So when you switch to the analysis settings, you can select the column by which the UT sorts. So in this case, if we wanted to find the coldest zone, we would sort by not the overall result score that's initially selected, but you would select lower offset as a criterion, as a column to sort by. So now analyze again, and then you see the results here, 5207 and 5213 with a score of 2.1 and 1.8. Looking at Excel, there we are, 5207 with a score of 2.1. So same result. Excel might be a little bit easier to view or easier to print. So looking at 5207, let's take another look at the template graph. So this should be our coldest zone. And we can clearly see in the purple chart there at the bottom, low values, and at the top, heating and cooling, dampers appear to be hunting. So maybe the zone is unstable, but certainly the results are too cold, no question about that. So their values like 66, 67 degrees down here. So obviously that is going to cause comfort complaints. But it means that we can find in a couple of minutes, even with a very large building, using the Setpoint analysis, we can browse through hundreds of zones in maybe 10-15 minutes, look at the results, do a little bit of error checking to ensure that we have the right zones, and then we go back to Excel, maybe look at the first few rows here, and as soon as we're down to error values of 0.3, 0.4, it basically means we have well-behaved zones. So that tells us that in the entire building there's only a handful of performers that need attention, and that's all we need to finish our report. One other thing we want to look at though is the airflows. We talked about temperatures and airflows, so we're going to do that in the last video in this series for Setpoint analysis.